Alright, hi everyone, welcome to my YouTube channel, City of Electrons. So in this video, we are going to do this. We are going to draw the model for that circuit, that is obtaining the AC equivalent of a network, which of course is the model of the network. And we say we are doing the RA model for this video, okay, for this series. So we are working with a common emitter fixed bias. Now, recall that this series is for electronic device and circuit 2. Okay, electronic device and circuit 2. Of course, circuit 1 we'll talk about like how we got to this point and why is this common fixed configuration bias. But of course, that's not what we are doing in this video. Okay, we are already in electronic device and circuit 2. And if you watch the introduction to class recap to this series of videos, you will observe that this is the second semester. So I started this thing from second semester. So I just hope it's still helpful somehow. Okay. All right. So the first step is set all DC sources to 0 and replace them by a short circuit equivalent. Now, this is what happens. What that means is replace everything with 0. Replace all DC source with 0. That means this guy will be out of the game. That guy will be out of the game. So this place will be out. Okay. So we are going to have same circuit. Okay, but it's going to look like this. Yeah, it's going to look like this. So what this means, look at it. This is exactly the same. But this is already step 1 and step 2. Let me show you step 1 here. So the step 1 here is this. I said remove all DC source, right? So formerly we had this RB facing up and it's connected to VCC. Okay, we had something like this. Let me use a different color so it will be visible. We had something like this. Yeah, this guy here. We had this guy here, okay, and then it was connected to this one on top, and then we had something here and this guy here. Okay, so looking at this guy now, since we took out this part, which is this, this thing that was here, which is this RB, came down here. You can put it on top, it doesn't really mean, but we just point everything down so that we know it's going to ground. Okay, so this same RB is this same RB, just that since we cut off this part, we just bend it downwards to face ground, like connected to ground, or 0, no voltage source there. So it's the same thing there. Hope that's clear. And then our ROC also, you can see ROC down. Clear. This E is the same thing here, E. Okay, then this V out is this V out, this V in is this V in. But there is another thing, which is this: replace all capacitor by a short circuit equivalent. That has been done already. So all capacitor by a short circuit equivalent. Note that this is in DC, this is in DC, and this is in AC. Okay, so of course in DC capacitors act as open circuit, but in AC they act as short circuit. Okay, so yeah, so look at this point. After VI we had the capacitor here, so it's an open circuit here. But for the AC domain now, or in the AC form now, that capacitor now is replaced with just a normal line, like one straight line. You see the capacitor is out here, same thing applies here. Capacitor 2 is out here, capacitor 2 is out, so your V out or V0 just goes in straight. Okay, so I hope that's clear. Then go to the next step. Remove all elements bypassed by the short circuit equivalent. We've done that. That is done already. all elements that is bypassed has been removed. Here you can't, the C1, there's no C1 here now, so the capacitor has been removed. The capacitor C2, there's no C2 here now, it has been removed. Okay? Then redraw the network in a more convenient form. So this is the network in a more convenient form. Okay, that's a network in a more convenient. Let me leave this AC here. AC in a more convenient form. Now the last thing to do, since we have it in this form now, the last thing to do is to put this in the form of RE model. Okay, because what we have now is just, we still have the transistor here. So the RE model, we have to take out the transistor. So this same circuit now, watch this. Okay, so I'll try and draw this. It might take a while, but let me just try. Okay, so what I want to see the drawing. I want to see the previous drawing. Okay, let's go. So of course we have our V in, which is this. Okay, and our current is there, which is I in. Okay, and then we also have this RB there. You see, I'm following what we have on RB, no magic. RB, I think it should be small letter because we're in the AC domain now. RB, that B is funny. I think I should zoom closer. Okay, RB. All right, and then at this point, this is where we had our base now. So this is the base current, IB. The base current will be there. Okay, no magic. Then everything is all right. Then of course, and this guy goes back, and there is something known as our impedance in. Okay, impedance in. Okay, of course we're talking about AC now, meaning the AC domain has impedance. Of course, we work with impedance. Then at this point, good. So at this point, pardon how my resistor look like. We are going to have what? Our impedance, because that's resistance. So all the resistance here, like all the resistance here is the impedance in. This resistance is, of course, impedance is still in ohms. Okay, that's what we have here. Okay, now this part, now we are trying to represent what we have here in this part here. Okay, and then what's next? The E. Okay, this is the E down here. This is the E down here. Okay, of course to earth or ground. And then we'll have this, which is current. Okay, and this current is the collector current. This is the collector current, small letter, collector current, IC. So if you check up, you will see, of course, this is the collector current now. The current is coming through this way, is collector current. The current is coming from this way, which is from this side. From this way is the base current. Is the base current. The current coming from this way is the collector current. Is the collector current. Okay. Clear now? I hope we are together. So it's just like this part is for this part. This part is for this part. This down is for this down. Okay, so progressing right now. Okay, what's next? What am I missing? I've done collector current. Yes, I've done that. Okay, then the next thing is this. We have this. Remember, we had this is impedance out in, right? We're also going to have impedance out. This O. Okay, and then what else? This one, we need that one too. That one too will also be there, which is this RC, and then VO, of course, and then we can place our collector current here. Sorry, not that way, like this, collector current. Okay, and then of course this represents our Z out. Good. So, but I have to. So this is kind of the form of the RE model, like this part of it. Let me even see if I can mark that. This part of it. Okay, that's part of it. Because the RE will be here. Now there's some calculation we have to make, but I will use, because this, if you check on maybe some textbook, you will see that this thing is not impedance I, and this is not this. The rest part, even this one, is something else here. So I will do the calculation and show you why we have something else here and what is supposed to be here. So we'll do that now. Now, of course, our impedance in is the same. Our impedance in is the same as what? Let me put this here. So for Zi, it's the same thing as VI. Why? Remember, from Ohm's law, VI equals IR. And in this case now, the R is the impedance. Of course, we know that R is impedance here. Then why do we have this here? V equals IR, that's correct. So if we just, so what's the value, or what's the value for, or formula for the impedance? That will be to move this guy down here. Okay, so if we're talking about impedance I, then this will be I and this will be I. That's exactly what we have here. Okay, all right. So, and of course our voltage in is what at this point, looking at this, our voltage in at this point is VBE. Okay, is the voltage between the base and the emitter, so VBE. So what we have here is actually VBE. Okay, over the input current. The input current is what? Look at it. The input current, I think I should take this thing closer to ourselves instead of moving back and forth. Closer to somewhere here will do better. Okay, so VB I, that's the current in, is what? Is our base current. At this point, the current in here is the base current. So we have IB. Great. So then what's the value for VBE? Of course, it is the emitter current multiplied by the internal resistance. Okay, I have it here already. So the transistor, yes, there's an internal resistance here. So that internal, because you know voltage is the same thing as current times resistance. So if you do not know the voltage at a point, take the current at that point and multiply it by the resistance at that point. Okay, so we can now say VBE is IE divided IE multiplied by what? RE. Now here comes the RE model. Here is the RE now we're talking about. So this RE is the internal resistance of our transistor. Okay, just bear that in mind. Just bear that in mind. It represents the internal resistance and then the emitter currents. Okay, because it depends on the emitter currents. So divided by IB. Okay, we're progressing. So let's just keep this thing as equation something. Keep that in mind. Keep that in mind somewhere. Oh no. Yeah. Good. So hold this in mind somewhere as equation 1. Okay. Now, for IE, recall that IE is the sum of voltages, sum of all the voltages that flows from the collector and from the base into the emitter to get the emitter current. So IE is the same as saying IB plus IC. Hey, Jesus, what is this? God help me. I see better. And there is a, okay, so yeah, that's that. Then also recall that this guy IC has a relationship with IB, which is an IC equals beta IB. So this can be written as IB plus IC is beta IB. This is the value for IC, okay? Or the relationship with IC. So this will now result in is this correct? Yeah, it's correct. So this will now result in, we say IB plus beta IB, which can be written as 1 plus beta, or factor out IB, okay? IB. Good. We're progressing. Now, the thing is, beta is great. Far, the value of beta is very, very large. Okay? So, when we say beta being very large, we can say, even when you add 1 to something that is really, really, really large, the 1 doesn't appear significant anymore, because the other value, which is B, is very large. So in that case, we can say that B, or this, where did I put this? Let me just put it here. 1, 2. Saying where, okay, let me just type that in. Where beta is very large. Good. So where beta is very large, IE equals beta IB. Hey, this is my IB. Beta IB. Okay. Good. I hope we're getting it. So, what happens next? Now, we can take this value of beta I of, we can take this value and bring it into equation 1. Remember, we have this as equation 1. So here we have IE, we'll now have what? Beta IB. Okay, we'll now have beta IB. So therefore, we can now say, let's put this here. So substitute IE into equation 1. Okay, So that will now give us Zi equals beta IB RE all over what? IB. I guess that's correct. Please confirm. Check it. Watch your screen. Watch your screen. Correct. Okay. So obviously, this guy can take out this guy. So what will be left is this equals beta RE. Good. Good. That means where we have Zi in our equivalent circuit, we are going to put beta RE. So we'll come here and we'll put beta RE, representing the RE model. Good. Okay. For those of you that have been watching my video for some time now, you know usually I solve with this color of pen. It doesn't really matter which color, but since this is kind of outside it, that's why I use this different color, because normally I'm supposed to go straight to determining the important parameters, but I just want to show us how we got this value here, because if you check some textbook, this is what you will see, not Zi. This is what you see. So that's why I say let me just go through the process. Okay. Then of course you also see something else here in some textbook, of which we have derived already. In the process of looking for this, we have gotten this already. I'll show you. Like right here, just look at it. IC. Look for IC here. IC. Look at it. IC. You see? IC equals beta IB. So just replace that here. So we now have beta IB. This is what you see in some textbooks. Okay? And of course, this also, you see something else there. Okay, so for this is the like this thing was gotten from the idea of a two-port network, meaning we have a terminal here, negative and positive, that's input, a terminal here, and then another terminal here. So this is kind of the system, okay, where we have our transistor, the RE model representing the characteristics and behavior of the transistor, the operating point and things like that, operating region. This point is is regarded as a system, while we have two-port network, that's a terminal here, positive and negative, another terminal here, positive and negative. Not usually you should have the like input coming this way, output going this way. But if you look at our arrow, you see the input is coming out here, it's coming in here. The output, which is supposed to go this way, is coming in. Now, for this, because we put our arrow this way, we are going to have a minus sign when doing our calculation. Bear that in mind. Okay, we'll bring this back when doing a calculation. Now, one thing to note. Okay, so the first time I just drew this thing like basic approach. Okay, they were now begin to place what is supposed to be there by on the calculation and basic understanding. Okay, now what we are going to add again or take out is this right here. Why? This is an RE model, and for an RE model, it does not include an output impedance. Okay, it does not include an output impedance. So there is this thing about the graphical method and slope, but I want to spare you all that in this video. Just bear in mind that the RE model does not include output impedance in this diagram. So therefore, this guy is going out. So what are we going to have there? R0. I'm going to have R0. However, we can calculate what our output impedance will be. Okay, so To calculate our output impedance, let me use the blue there so that we know I included this. Okay, so if you look at textbook, this is what you see. Okay, so at least close to this in terms of notations and things like that. So with this, we've been able to draw the model for our circuit. Okay, for our transistor, we've been able to draw the model. So this is the transistor, and we move step by step to this point, and then first of all, then after that, I drew it as basic as we can get before including these parts that appear a bit complex to get. Okay, so yeah. So I guess this is quite helpful. And in the next video, okay, so I hope this is helpful. I hope this is helpful. Okay, so what we just did is follow this process here, like how to obtain it. So we set all DC source to 0 and replace them by short circuit equivalent, and we replace all the capacitor by short circuit equivalent, and we remove all the elements and bypass by the short circuit equivalent, and then we redrew the network in a more convenient form. So that's how we got from this point to this point, and then from this point we just drew the whole thing, like we drawing everything again. But when we got to this part, we replace it with this, and I demonstrated how we got that right here, and also how we got this and then this from a principle that the ROE model does not have an output impedance here in this diagram. However, we can calculate it, and that's what we are going to start with in our next video. How do we calculate this guy, the output impedance? So there are some important parameters we are going to calculate, which is the output impedance, calculate this guy, and then even the input impedance. Okay, I think we've done that already. Yeah, we've done that already. Okay, and then the gain, and then some other parameters we are going to calculate in the next video. So hope this was helpful. Like, share, subscribe, comment, and I'll see you in the next video. Thanks for watching.